methods in civil engineering, we will continue our discussion on linear systems which we talked about last time. Last time we ended our lecture talking about the need for pivoting. We found that most matrices, if we have to perform Gaussian elimination on those matrices to solve the linear system successfully, they require pivoting. However, today we will concentrate on types of matrices which do not need pivoting. There are two types of special matrices which do not require any pivoting, that is, they can be reduced to triangular form without any row or column interchanges. A diagonally dominant matrix, that is a matrix with components aii, diagonal elements aii, such that each diagonal element is greater than the sum of the absolute magnitudes of the off diagonal elements, is known as a diagonally dominant matrix. It always has the largest elements on its diagonal, thus no row or column interchanges can improve the natural pivot, that is the diagonal element. Since the diagonal element is the largest element in the row, it always is assured to be non-zero. Another type of matrix which does not need any pivoting is a symmetric positive definite matrix. A positive definite matrix is defined such that it is symmetric. First of all, a symmetric positive definite matrix by definition is symmetric, which means that A transpose is equal to A, and in addition X transpose A x is greater than 0 for all x not equal to 0. Given any arbitrary vector x and given that that vector is not identically equal to 0, we can be assured that if we perform the operation x transpose A x, we are going to get a positive number for a positive definite matrix. So, for these two types of matrices, we do not need any pivoting while performing Gaussian elimination. We will talk about positive definite matrices in a lot of detail, because in many civil engineering applications we encounter positive definite symmetric positive definite matrices. First, let us talk in more detail about symmetric matrices. We will come back to talk about positive definite matrices further on in the lecture. Let A is equal to Aij with components Aij be a symmetric matrix, which obviously means that Aij is equal to Aj, that is, elements on either side of the principal diagonals are mirror images of each other. That is, if we change the row and column, we are going to get, if we transpose the row and column, we are going to get identical elements of the matrix. So, Aij is equal to Aj for all I equal to 1 to n, j equal to 1 to n. If Gaussian elimination is performed without row or column interchanges at every step k, we can be assured that the matrix is going to remain symmetric. That is, Aij after the kth step is going to be equal to Aji after the kth step. So, for a symmetric matrix, if we perform Gaussian elimination, that is, if we are able to perform Gaussian elimination without any row or column interchanges, we can be assured that at every step the matrix is going to be symmetric. So, at every step the matrices of order n plus 1 minus k for k equal to 2 through n are going to be symmetric. According to the elimination algorithm, let us go back to the elimination algorithm which we derived last time for Gaussian matrices, for Gaussian elimination. According to that elimination algorithm, at any step k plus 1, the transformed element Aij k plus 1 is given in terms of the elements at step k according to the following relationship. Aij at k plus 1 is equal to Aij at k minus Aik at k times Akj at k divided by AKK of k. We encountered this equation, this transformation relation in our last lecture. From the symmetry of the transformed matrix at step k, we can write Aij at step k plus 1 is equal to Aj at step k. Please note the difference between these two equations. In the first equation, we had Aij k at the right, on the right hand side. In the second equation, in that we use symmetry to write Aij in terms of Aj. So, we replace Aijk by Ajik. Similarly, we replace Aikk by Akik and Akjk by Ajkk. So, these two expressions are identical for symmetric matrices. So, this tells us that if the transform matrix at step k is symmetric, the transform matrix at step k plus 1 is also bound to be symmetric, because this expression is identically equal to Aj k plus 1. Since Aj k plus 1 is equal to Aij k plus 1, that means at step k plus 1 also the transformation matrix is symmetric. This is Aj k plus 1 by definition, but since at k equal to 1 the starting matrix is by definition symmetric, that is because our initial matrix was symmetric. So, our starting matrix is by definition symmetric. The transform matrix must be symmetric for all k equal to 1, 2 through n. Why is that? Because our starting matrix is symmetric, and we have shown that if at step k my transformation matrix is symmetric, at step k plus 1 it is bound to be symmetric. So, at k equal to 1, if it starts with a symmetric matrix, that is at k equal to 1 it is symmetric, then it is obvious that at k equal to 2 it is going to be symmetric, at k equal to 3 it is going to be symmetric, and it is going to be symmetric through all the steps of the Gaussian elimination. Because of the symmetry of the transformed matrix at every step k, we only have to compute and store terms in AK on or above the main diagonal. The advantage of symmetry is this: it reduces drastically the storage required. So, since the matrix is symmetric, since at each stage the transformation matrix is symmetric, we will take advantage of symmetry and store only the terms above the main diagonal. We will no longer store the whole matrix. So, this automatically reduces the storage requirement by 2. Thus, for symmetric Gaussian elimination, the transformation rule becomes Aij k plus 1 is equal to Aij k minus Aki k Akj k divided by Akk kk. As you can see from the previous slide, this is basically identical to what we obtained in the previous slide, except you note that we are now taking I is equal to k plus 1 through n and j is equal to I through n, which is basically we are doing the computations only for the 1/2 of the matrix, right. We have reduced the number of operations. The number of operations is approximately halved from n cube by 3 to n cube by 6. In addition, nearly half the memory is saved. So, we are performing the operations only on the elements which are above the main diagonal, and we are also storing only half the previous, the storage is also half the previous storage. However, we should enter a word of caution here. It is not always possible to perform Gaussian elimination on symmetric matrices without pivoting. Symmetry is preserved. We note that symmetry is preserved if only if we perform the Gaussian elimination on a symmetric matrix without performing any row or column interchanges, right. So, this is only possible if we do pivoting on a diagonal element. either this is possible only in two situations, either we perform Gaussian elimination without performing any row or column interchanges, or we do pivoting on a diagonal element, and when we do pivoting on a diagonal element we do complete pivoting, that is we interchange both the rows and the columns to preserve the symmetry of the matrix. So, either we do not do any pivoting at all, or we do complete pivoting on the diagonal elements. If we do partial pivoting, which just involves a row interchange, we will destroy the symmetry of the matrix. Thus, symmetric Gaussian elimination cannot be used on all symmetric matrices. It is important to note that symmetric Gaussian elimination cannot be used on all symmetric matrices, particularly when we encounter elements on the pivot which are either 0 or too small. We have to go for pivoting, and in that case if we do partial pivoting we are going to destroy the symmetry. The only occasion when we can preserve the symmetry is if we do pivoting on a diagonal element and then we do total pivoting, that is we interchange the rows as well as the columns. However, this is where the advantage of positive definite matrices come in, because it can be shown that for positive definite matrices Gaussian elimination without pivoting is always stable. There is absolutely no need to do any pivoting for positive definite symmetric matrices. In that case, symmetry can always be preserved and the number of operations and storage can be halved as discussed earlier. There is a simple criterion known as Sylvester's criterion, which enables us to determine whether a matrix is positive, whether a symmetric matrix is positive definite or not. According to this criterion, a symmetric n by n matrix, a symmetric matrix A with n rows and n columns, is positive definite if and only if, that is, it is a necessary and sufficient condition, that the determinant of A k must be greater than 0 for all k equal to 1 to n, where k A k is the k by k matrix formed by the intersection of the first k rows and k columns. So, we basically look at a series of sub matrices starting with k equal to 1, which is basically just the element A11. Then with k equal to 2, we are basically looking at the elements of the first row and the first column, the square matrix formed by the intersection of the first row and the first column, which is going to be a 2 by 2 matrix with elements A11, A12, A21, 222. Similarly, for k equal to 3, we look at the square matrix formed by the intersection of the first 3 rows and 3 columns with elements A11, A12, A13, A21, A22, A23, A31, A32, A33. If all these sub matrices turn out to have positive determinants, if all those determinants are positive, then the symmetric matrix is going to be positive definite. In that case, symmetry will always be preserved by Gaussian elimination, and the number of operations can be reduced from n cube by 3 to n cube by 6 as we discussed earlier. Similarly, the storage too can be halved. It can be shown that if a symmetric matrix satisfies Sylvester's criterion, that is, it is positive definite, it is assured to have all its pivots positive, that is A k k k, k is equal to 1 through n is always going to be greater than 0. That is, all these pivots A k k with superscript k, k equal to 1 through n are going to be greater than 0. This can be shown by something known as LU decomposition. If it is possible to decompose the coefficient matrix A into the product of a lower triangular and an upper triangular matrix, that is A is equal to LU, Recall what is a lower triangular matrix. A lower triangular matrix has got elements which are above the principal diagonal 0. It has got elements, non-zero elements only below or at the principal diagonal, while an upper triangular matrix is a matrix which has got elements above the at or above the principal diagonal greater than 0, while all elements below the principal diagonal are 0. So, if it is possible to decompose the coefficient matrix A into the product of a lower triangular and upper triangular matrix, that is A is equal to LU, then the system AX can be written as Ly equal to B, where y is an intermediate variable, Ly equal to B and Ux equal to y. So, basically Ax equal to B is basically Lux equal to B. We denote Ux equal to y, and we solve the system Ly equal to B to determine y, and then we again solve the system Ux equal to y to determine x. So, instead of solving Ax equal to B at one go, we are solving two triangular systems. First, we are solving the system Ly equal to B to determine y, and then we are solving the system Ux equal to y to determine x. But each of these solution of these triangular systems, as we have seen earlier, is very simple. It just involves back or forward substitution. Since solving a triangular system requires half n square operations, basically the number of operations in a typical back substitution operation, if the decomposition A is equal to LU is known a priori, solving the system Ax equal to B would only require 2 times n square by 2 is equal to n square operations. Basically, we will solve the system Ax equal to B by solving the system Ly equal to B, which is a triangular system which would require n square by 2 operations. Similarly, solving the system Ux equal to y is again going to require another n square by 2 operations. So, the total number of operations is equal to 2 times n square by 2 is equal to n square. This of course assumes that we know the decomposition. The decomposition of A into LU is known a priori, is known beforehand. If we compare the number of operations n square to the number of operations required for Gaussian elimination, which is n cubed by 3, the advantages of LU decomposition for large systems is obvious. So, if we can perform the LU decomposition, then we can solve the equation just by, we can solve repeated systems Ax of the type Ax equal to B by just performing n square operations. The LU theorem states that if A is an n by n matrix and Ak denotes the k by k matrix formed by the intersection of the first k rows and k columns of A, then if determinant of Ak is not equal to 0 for k equal to 1 through n minus 1, then there exists a unique lower triangular matrix L with components denoted by Mij and with diagonal components Mii equal to 1, and a unique upper triangular matrix U with components Uij, so that Lu is equal to A. So, let us take a look at it again. It says that if A is an n by n matrix and Ak is the k by k submatrix formed by the intersection of the first k rows and k columns of A, and if the determinant Ak is not equal to 0 for k equal to 1 through n minus 1, then there exists a unique lower triangular matrix L with components Mij and with diagonal components Mii equal to 1, and a unique upper triangular matrix U with components Uij, so that LU is equal to A. So, what this tells me is that if these conditions are satisfied, that is if all the AKs have positive determinant, then there are unique matrices, upper triangular and lower triangular matrices U and L, such that A can be written as LU equal to A. How can we show this? Well, this can be shown quite easily by induction. Suppose the matrix is of size 1, which is basically it is a scalar. In that case, the decomposition is obvious, because we have assumed that the diagonal elements of the lower triangular matrix L are 1, right. So, it is obvious that the upper triangular matrix is now just A11, and obviously this decomposition is unique. Now, suppose the theorem is true for n equal to k minus 1, for any k, right. So, let us suppose that it is true for k minus 1, then for k, for n equal to k, we can partition a k into the following. A k can be written as a k minus 1, which is the a k minus 1 denoting the part which is formed by the intersection of the first k minus 1 rows and k minus 1 columns of my original matrix, and the remaining part, which is B is a B and C comprising column vectors with k minus 1 components. So, B is a column vector with a minus 1 components, C transpose is a column vector, C transpose is actually a row vector with k minus 1 components, and then the diagonal term AKK. Now, we know that since AK minus 1 satisfies the LU theorem, we can write AK minus 1 is equal to LK minus 1 times product with UK minus 1, where LK minus 1 and UK minus 1 are the unique lower and upper triangular matrices corresponding to the LU decomposition of AK minus 1. Since AK minus 1 satisfies the LU theorem, we know basically that there is an LK minus 1, unique LK minus 1 and a unique UK minus 1, such that AK minus 1 is equal to LK minus 1 product UK minus 1. Since determinant of LK minus 1 times determinant of UK minus 1 is equal to determinant of AK minus 1, because the product of two matrices is equal to the product of their determinants, and since we know that determinant of AK minus 1 is not equal to 0, it obviously means that both UK minus 1 and LK minus 1 have non-zero determinants. Since the product of these two numbers, determinant of LK minus 1 and determinant of UK minus 1 is greater than 0, it is obvious that none of these individual numbers can be 0. So, each of these matrices LK minus 1 and UK minus 1 have positive determinant, which means they are non-singular and they can be inverted. Thus, if we can write AK minus 1 B C transpose AKK as LK minus 1 0 M transpose 1 times UK minus 1 U 0 UKK. Note the form of these matrices on the right hand side. The first matrix is of the form of a lower triangular matrix, because all the elements above the principal diagonal are 0, while the second element on the right hand side is as an upper triangular matrix, because all the elements below the principal diagonal are 0. So, we are saying that if AK minus 1 has an LU decomposition, then we can write AK in terms of the product of these two matrices, provided that LK minus 1 U is equal to B. Basically, LK minus 1 operating on this row, LK minus 1 0 operating on this row U U K K. So, basically LK minus 1 U is equal to B, M transpose UK minus 1 equal to C transpose. So, basically it is this row operating on this column gives me C transpose, and M transpose U plus UKK is equal to AKK. So, if these conditions are satisfied, then we can write this matrix AK in terms of two lower in terms of a lower triangular and an upper triangular matrix. But since we know that Lk minus 1 and Uk minus 1 are non-singular, that means that if we try to solve this equation Lk minus 1 u equal to b, or for that matter this equation M transpose Uk minus 1 equal to C transpose, since Lk minus 1 is non-singular, Uk minus 1 is non-singular, that means that we can always solve this system and get the appropriate values for M and U. So, once we have determined U and M uniquely, UKK can be uniquely determined from AKK minus M transpose U. Thus, if the decomposition AK minus 1 is equal to LK minus 1 UK minus 1 exists, then the decomposition AK is equal to LK UK also exists and is unique. So, what is the meaning of this? We have seen that for A1 is just a scalar, right, and the submatrix formed by the intersection of the first row and the first column, and for that submatrix we have shown that an LU decomposition trivially exists with the L component equal to 1 and the U component just equal to A11 itself. So, since the LU decomposition exists for k equal to 1, and we have shown that if the LU decomposition exists for k minus 1, it also exists for k. So, if it exists for k equal to 1, it exists for k equal to 2. Since it exists for k equal to 2, it also exists for k equal to 3, and so on and so forth. So, if the condition that determinant AK is greater than 0 is satisfied, then the LU decomposition exists for any matrix A of size n by n. For any non-singular matrix Ka, in case one of the AKK k equal to 1 through n minus 1 have a 0 determinant, it is possible to reorder the rows to ensure that the LU decomposition exists. Why? Because what we are saying is that the LU decomposition is going to exist is if each of those submatrices AK have a positive determinant. Now, if it so happens that in one matrix A, which is non-singular, for non-singular matrix A, one of the k by k submatrices, suppose of some order, have a 0 determinant, then it is possible to reorder the matrix, to reorder the rows to ensure that that k by k submatrix no longer has a 0 determinant, that is, it has a positive determinant. So, they can basically, by interchanging the rows, we can ensure that for any non-singular matrix, all the submatrices AK k equal to 1 through n minus 1 have a non-zero determinant, which means that the LU decomposition is going to exist for that matrix, and each of these L and U matrices are going to be unique. How can we show this? Well, this can be shown from the equivalence. We can show that there is an equivalence between Gaussian elimination and LU decomposition. That is, if we perform Gaussian elimination on a matrix without any row or column interchanges, we are going to get very close to the LU decomposition, barring a minor modification. So, basically what we are saying is that if we take a matrix A n by n, and suppose we can perform Gaussian elimination on that matrix without performing any row or column interchanges, in that case it is possible to recover the LU decomposition of A with just a minor modification. We want to show the equivalence of LU decomposition with Gaussian elimination. In order to do this, we consider the evolution of a certain element aij in my original matrix during Gaussian elimination. If aij is on or above the principal diagonal, that is I is less than or equal to j, that is the column index is always higher than the row index, in that case aij stops evolving, that is it gets frozen at its value after the ith step of the elimination, because after the ith step that element is it has reached its final value, it does not change any further. So, aij is equal to aij plus 1 through aij n, where the superscript now denotes the various steps in the Gaussian elimination. Similarly, if aij is below the principal diagonal, that is if I is greater than j, that is its row index is greater than the value of the column index, then aij becomes 0 after the jth step of the elimination, because recall at the end of the Gaussian elimination what are we going to get? We are going to get an upper triangular matrix, which means that the elements below the principal diagonal are all going to be 0, and any aij reaches its final value 0 value after the jth step of the elimination. So, aij j plus 1 is equal to 0, and it is going to remain 0 for the j plus 2 through j plus 3 through nth step. This means that any aij is only transformed for the first r steps in the elimination, where r is the smaller of I minus 1 and j, I being the row index and j being the column index, following which its value is frozen. So, basically we are combining these two statements, that if aij is on or above the principal diagonal, it stops evolving after the ith step of the elimination, and if aij is below the principal diagonal, it stops evolving after the jth step of the elimination, and noting that I is the row index and j is the column index, we are combining these two statements together and making this new statement that aij only changes for the first r steps in the elimination, where r is the smaller of I minus 1 and j, following which its value is frozen. Let us go back to the transformation rule for Gaussian elimination, which is, let us recall, aij k plus 1 is equal to aij minus the multiplier mik times akj k, where the multiplier mik, if we recall, is nothing but aki divided by akk. So, let us look at this equation and we sum the values over k equal to 1 through r. So, apply a summation on both sides for k equal to 1 through r, and then so basically we are just taking this equation and summing it for k equal to 1 to r to get this expression. Nothing changes, we have just added a summation sign in front, and we are performing the summation for k equal to 1 to r. Why are we performing summation for up to r only? Because we know that after r, when k goes beyond r, the elements do not change at all. So, we are performing the summation for the first r steps of the Gaussian elimination. If we cancel the terms on the left hand side, how can we cancel the terms? If you look at the left hand side, you can see that this minus this, right. So, all the terms will cancel out except the r contribution from this term aij r plus 1 and the k equal to 1 contribution for this term, which is going to be aij 1. Otherwise, for instance, for k equal to 1 here, we are going to get aij 2, and this is going to cancel out from the aij 2 contribution from the second term. So, the only terms which are going to survive are going to be aij r plus 1 and aij. So, that gives me my left hand side. The right hand side remains identical, which is equal to minus k equal to minus summation k equal to 1 through r mik akj k. Since aij r plus 1 is equal to 0 for I greater than j, recall that all the terms which are below the principal diagonal are going to become 0 at the end of Gaussian elimination. So, when r is when for r plus 1 aij r plus 1 is going to be 0 for I greater than j. So, we can get rid of the aij r plus 1 on the left hand side in the first equation, and we can write this equation as aij is equal to summation of over k equal to 1 to j of mik akj k for I greater than j. Again, let us recall that for I lesser than or equal to j, that is for elements above the principal diagonal, aij r plus 1 is equal to aij I, that is it gets frozen at its value at aij I, right. Then we can write aij is equal to aij I plus sigma mik akj k, k is equal to 1 through I minus 1, which we can combine these two terms together and write it as sigma k equal to 1 through I mik akj k, if we assume that for aii mii is equal to 1. So, we are putting these two terms together and writing it within the summation and extending the summation index from I minus 1 to I. So, we can combine these two expressions. We can combine this expression and that expression, right. We can combine this expression and that expression to get this expression aij is equal to sigma k is equal to 1 to p mik akj k, where p is the smaller of I and j. So, p is equal to j in this case, right, and p is equal to I in this case. So, we are combining these two expressions together to get this expression. From this expression, if we look at the contributions of mik, it is clear that mik is we are only using the values of mik that are, if we consider mik to be representing a matrix M, mik being the components of a matrix M, it is clear from this expression that we are using only the components of M which are at or below the principal diagonal. Why? Because mik, k is summed from, k goes from 1 to p, and p is again the minimum of I and j. So, j cannot exceed I, right. So, it is p is equal to minimum of I and j. So, the second index here k, which is denoting the column index, cannot be more than the row index. So, that means that since the column index cannot be more than the row index, that means we are only considering the elements of mik which are at or below the principal diagonal. So, if we take these elements mik and then on the elements above the principal diagonal we make those elements 0, then this matrix M becomes a lower triangular matrix, and we can denote it as L, which is the notation for a lower triangular matrix. Similarly, it is clear that akj define the elements at and above the principal diagonal. Why is that? Let us consider the term akj. Akj, and it is clear that k cannot be, k is being summed from 1 to p, and k cannot be greater than, p cannot be greater than j, right. So basically the first index, the row index cannot be greater than the column index. The row index cannot be greater than the column index. That means that we are only concerned with the with AKJ which are at or above the principal diagonal. So again, if we assume that the elements of AKJ below the principal diagonal are 0, in that case we can write AKJK as a upper triangular matrix. Similarly, it is clear that AKJK define the elements at and above the principal diagonals of a matrix, and if we define the elements below the principal diagonal of this matrix to be 0, it is clear that U, where we have used U to denote the matrix comprising the components AKJ, U is an upper triangular matrix. Hence, we can rewrite our previous equation Aij equal to summation k equal to 1 to p mik AKJ k as the product of a lower triangular and an upper triangular matrix. And since recall that this expression that we obtained was from our usual Gaussian elimination, we did not do anything special to get here, right. So, this is what we get after Gaussian elimination, and we can see that can be written as in terms of the product of an upper triangular and a lower triangular matrix, provided that in the Gaussian elimination, in the normal Gaussian elimination, we just stored the upper triangular part, but now in the lower triangle, in the part below the principal diagonal, which in usual Gaussian elimination is 0, if instead of making it 0, we stored these multipliers, mik, then after Gaussian elimination we are going to recover our LU decomposition barring the trivial diagonal elements of L, which are always equal to 1. Thus, if we perform Gaussian elimination on a matrix A, we automatically get its LU decomposition also. Typically, the elements below the principal diagonal of A are used to store the multipliers other than the trivial diagonal elements of L, while the elements on or above the principal diagonal are used to store the usual upper triangular matrix of Gaussian obtained at the end of Gaussian elimination. Thus, LU decomposition does not require any additional storage. So, basically if we overwrite our original matrix after storing the upper triangular elements above or below the principal diagonal and use the elements below the principal diagonal to store the multipliers, we are automatically going to get our LU decomposition. Recall that if the k by k matrix formed by the first k rows and k columns of A, AK, has a positive determinant, then we can write AK is equal to LK UK, where LK and UK are lower and upper triangular matrix. Also, let us remember that determinant of AK is equal to determinant of LK times determinant of UK. So, the product of determinants is equal to the determinant of the products. But we have seen that the determinant of LK is equal to 1. Why is that? Because all the diagonal elements of L are identically equal to 1, and we have seen in a previous lecture that the determinant of a triangular matrix is nothing but the product of its diagonal elements. Since all the diagonal elements are 1, determinant of LK is equal to 1, and determinant of UK is again the product of its diagonal elements, and its diagonal elements A11, A22k, A33k, etc. are nothing but the pivots in the Gaussian elimination. So, the determinant of UK is nothing but the product of the first k pivots. So, Gaussian elimination can be carried out without row or column interchanges if each of those pivots is different from 0. So, basically if each of these pivots is different from 0, then determinant of uk is going to be non-zero always. Determinant of ak therefore is also going to be always non-zero, because determinant of lk is always going to be 1 and determinant of uk is always going to be positive. Since determinant of ak is always going to be positive, what does that mean? That means this matrix is going to be positive definite, and since it is positive definite, it's for all if this determinant is greater than 0 for all case, then that matrix is positive definite, and in that case we can perform Gaussian elimination without the need to perform any pivoting. So, Gaussian elimination can be carried out without row or column interchanges if each of these pivot elements is different from 0. Each of these pivot elements different from 0 means uk has positive determinant, uk has positive determinant, lk by definition has positive determinant, the ak always has positive determinant. Thus, Gaussian elimination can be carried out without row or column interchanges if determinant of ak is not equal to 0. The resultant matrix, as we have seen, yields the LU decomposition if care is taken to store the multipliers mik below the principal diagonal. If one or more of the pivots become very small or are equal to 0, partial pivoting becomes necessary for stability. We have seen that, right? If any of the pivots, pivoting is not required only if each of these pivots is greater than 0. However, if one of the pivots becomes very small or actually becomes 0, then we have to do pivoting, right? It also means that the matrix is no longer positive definite, right? Then at the end of Gauss, if it so happens that the matrix is not positive definite and we have to perform pivoting, then at the end of Gaussian elimination if we take care to store the multipliers below the principal diagonal, we are still going to get an LU decomposition, but that LU decomposition that we are going to get is not going to be the LU decomposition of the original matrix A. It is going to be the LU decomposition of another matrix A star, where A star has been obtained by performing the same row interchanges performed on A. So, let me repeat. So, while we were performing Gaussian elimination on A, we found that in order to maintain the stability of the solution, we had to do some pivoting. So, we entertained certain rows of A, right, and then at the end of Gaussian elimination, we took care to store the multipliers below the principal diagonal. So, we got an LU decomposition, but the LU decomposition we got is not the LU decomposition of my original matrix A, it is the LU decomposition of another matrix A star, which can be obtained by performing the same row interchanges which we performed in the course of Gaussian elimination on my original matrix A. However, for a positive definite matrix, by definition each of my k by k submatrices k through n are assured to have positive determinant. Therefore, the pivots a11, a22, a33, an are each non-zero, and therefore Gaussian elimination can be performed with no interchanges. What does that mean? That means that if while performing Gaussian elimination we take care to store the multipliers at locations below the principal diagonal, then at the end of Gaussian elimination we are going to get an LU decomposition, and that LU decomposition is going to be the LU decomposition of my original matrix A. So, next we consider a more compact method for Gaussian elimination. This is known as Crout's method. This method allows determination of L and U directly while avoiding the need to store some of the intermediate results. As in the Gauss elimination, at the kth step we compute the kth column of L and the kth row of U. However, in Crout's method, the elements a I j for I j greater than k are left unchanged. How does that happen? Well, to see how that happens, let us recall our equation for Gaussian elimination in terms of LU components, which we obtained just a little while earlier, right, and which gave us basically the equivalence between Gaussian elimination and LU decomposition. Let us recall that equation, which says Aij is equal to product of Mik Ukj summed over k is equal to 1 to p, where p is the smaller of I and j. So, it is the smaller of the column of the row and the column index of Aij. We can think of this equation as n square equations, because I is going to vary from 1 to n, j is going to vary from 1 to n. So, there are going to be n square terms, right. So, this is basically, we can think of this as n square equations for the unknowns m and u, and we remember that m and u are the non-zero components of lower and upper triangular matrices. So, m and q have each n square by 2 terms. So, m has n square by 2 terms, u has n square by 2 terms. So, the total number of unknowns is n square by 2 plus n square by 2. So, we can think of this as n square equations for n square unknowns, where my unknowns are m and u, which are the components of the lower and upper triangular matrix. So, we can think of this equation as a set of n square equations for determining the unknown coefficients, unknown components of my lower and upper triangular matrix. For the kth step, the following equations can then be used to determine the kth row of U and the kth column of L. So, basically I am rewriting those same equations, but once I am assuming that j is greater than or equal to k, that is, I am trying to find akj such that j is greater than or equal to k. So, basically I am finding the components which are above the principal diagonal, right. Since j is greater than k, the column index is more than the row index. So, I am looking at terms above the principal diagonal, and that I can find by using this equation, but now the summation has changed, the limit of the summation has changed from p to k. Why is that? Because of this condition that j must be greater than or equal to k, and this condition that p is the minimum of I and j. Similarly, aik I can obtain from the previous equation, but now I am considering only I am trying to find the kth columns of L, and because of that I is greater than k. So, I am using the same equation as before, except that the limit of the sum is now k, right. The limit of the sum is now k, simply because I is greater than k, and let us recall from our previous equation, p is the smaller of I and j, p is the minimum of I and j, and since I is greater than k, p is equal to k, right. So, so now we are splitting the previous equation into two parts, and we will continue next time with this discussion and show that how it is using these equations it is possible to write ukj and mik in terms of the previous. So, you can these equations are this form. The Crout's method is useful because you can see these ukj and mik. To compute ukj and mik, I am only taking summing terms up to k minus 1, right. So, I am only using known terms, that is terms which are known up to the k minus 1th step. We will continue our discussion with Crout's method in our next lecture. Thank you very much.